morning. Let's start our lecture on heat transfer. So what is heat transfer? Huh? Anyone wants to volunteer a definition for heat transfer? Yes? Very good. Heat transfer is transferring heat from one component to another. What do? I transfer heat from hot, hot, to a cold substance. I don't take heat. I take a hot substance, I take a cold substance, and I transfer heat to a cold substance. So, why do we chemical engineers, going to be chemical engineers, you need to study heat transfer? Why? Why am I teaching you heat transfer? Yes, I want to teach you heat transfer. Any other reason? Yeah, reactions occur on different temperatures. One important reason is reactions occur at different temperatures. One other important reason is environment. Environment is a big issue these days, my friends. There are many environmental officers going around everywhere, checking factories. If you're in factories using more energy than it is norm to use, you will end up in a problem. So this book, Heat Transfer, will help you learn the concepts of heat transfer so that your employer doesn't end up in a problem with energy crisis. You have to be standardized the amount of energy you'll be requiring to govern the temperature of the reactions. So the word thing I've written here is heat transfer. Heat transfer is made up of two words, heat and transfer. Heat and transfer, those are the two words from which heat transfer is made. So, what is heat? Heat is energy. Very good. What is energy? New answer. Physically, energy is defined ability to do work. The ability to work. I don't think you have much energy, right? You don't have much ability to do work. You don't do much work, huh? This is an important word in heat transfer. A very, very important word in heat transfer. And now we'll be studying energy. First, before we begin heat transfer, we study energy. So, energy. There's one basic law of energy which you should know, and that is conservation of energy. Very good. That's what I was looking for, conservation of energy. Conservation of energy. That is, energy can neither be created nor destroyed. It can only be transferred from one form to another. So, I use the word form. What do you mean by form? How many forms of energy are there, huh? Any guesses? No guesses. We'll start discussing then. What all energy are there? There's one energy called, I would like to start with the definition of what we call as internal energy. What we call as internal energy Internal energy is the energy possessed by the water here. The water here, which I'm pointing to, it possesses some energy. Why? Because of the atoms inside it, it possesses energy. And this energy, which is possessed by it because of the atoms inside it, since the atoms are inside it, is called internal energy. The next energy we'll be studying is mechanical energy. Not studying, discussing right now is mechanical energy. What is mechanical energy? Energy to do mechanical work is called mechanical energy. As simple as that. Mechanical energy is of two types. Yes. Potential energy. Yes, potential energy and kinetic energy. So it is of two types: kinetic energy, kinetic, potential. Kinetic and potential. Kinetic and potential are two types of mechanical energies. Which are written here. So what is kinetic energy? Kinetic energy, let me demonstrate with this very bottle. This is kinetic energy. From here to here. Kinetic energy. It is the energy possessed due to motion given by half mu squared. Half mu squared gives you kinetic energy. Then the other part, which we are talking about, is the potential energy. Here we'll have to discuss some things like how do I define potential energy? MGH? No, that's not the right definition of potential energy. No. Okay, the right definition of potential energy is defined as potential energy is defined as the energy possessed by a body, for example, this water again, due to its relative position in a conservative field. Now, what I said, due to its relative position in a conservative field, what did I mean? I didn't mean that is it located in Mars or is it located in Jupiter or Saturn or I don't know where. It might be located anywhere, but what I mean is, first I have to define conservative field. Okay, so for conservative field, let us think about force. What is force? Push or pull. Very good. Oh, excellent students here. Why am I teaching them? I don't understand. Still, I continue. Push / pull is force. Force does not mediate by itself. It is said to mediate via fields. Force creates its fields, that is, the distance to which the effect can be felt. For example, if I'm putting force on this bottle, like this, the distance it can be felt is the whole area inside, the whole volume of the bottle can feel my force. So the force field is the area of the bottle, the volume of the bottle. That's my force field. Force fields are three-dimensional in nature. Now, some other force fields. So for example, the electrical force field. If I place an electron, if I think this to be an electron, and I place it here. Okay, I placed an electron at this point, so it's attracting all positive charge towards it and deflecting all any negative charge. So the force field is created in forms of spheres like this. This is sphere 1, sphere 2, sphere 3, sphere 4, this is sphere 4, sphere 5, and the field goes on. It's a very, very large field. Something larger field. A larger field is the field due to Earth's gravity, the gravitational field. Gravitational field is a very, very, very large field. Its effect is still large distances. Ah, gravitation. Since we are discussing gravitation, let me tell you an important point about gravitation. Ah, if I assume this is how Einstein describes gravitation. If I assume this to be my space-time, and I put a mass on it, a mass as in this, my space-time bends. Whoo, what's this? This is a very new thing for you all of you. Bending of space-time. This was my space-time, flat as it is, but then I had mass. I put mass and my space-time bends like this, and I put mass, my space-time bends. So, what does the bending of the space-time indicate? So, it indicates the gravitational field. If I have mass in space-time, it bends, and the amount of space-time it bends along with it is its gravitational field. For example, since this was bending this much of space-time, like this, it was quite good. It had quite a large gravitational field. And if I put anything in this bent space-time, it would go here, down. I think you can't see that, but that's what will happen. So that is gravitational field. So we defined many fields. We defined electrical field, we defined gravitational field, we even defined force field, force I applied. And we'll even define another field, that is the frictional field. Now this is what I want to say. I have here a bottle. I take the bottle and I throw it. It stops. Why did it stop? If Newton's first law is true, then any body moving with a velocity should continue moving with velocity until an external force acts on it. That means some force acted on it and that stopped it. Now, why didn't that force make it go backwards? Like if I have a force and that force stops the body, that force will eventually make the body go backwards. First it will retard, the body is coming, the force is in this direction, the body retard, and then the force will take over and the body will go here. So this is the force, this is the body going top, force takes over, body accelerates. Friction force is a very, very complex force. It is only there when there is relative motion. If there is no relative motion, there is no friction. So friction does not have a field, a well-defined field. For example, even this force of mine doesn't have a well-defined field, actually. So, friction and the force I applied on that bottle to squash it do not have any well-defined field. So what do I mean? So what? How do we? So what was I thinking about this? Only for conservative fields are the fields or forces which have a well-defined field. Only if you have a well-defined field is it a conservative force. So you have potential, as I told you, is the relative position of the object in a conservative field. So this bottle of mine again is placed in a gravitational field. The gravitational field which I explained, that curving space-time. Such a good phenomena, curving space-time. I want to show it again. I have here a space-time. I put this, it bends. That's what I call curving of space-time. So, potential energy is defined. We define internal energy, potential energy, kinetic energy. The next energy I want to define is nuclear energy. nuclear energy. Who is here who has not heard of the very famous, extremely famous phenomena concerned with nuclear energy, given as this? I don't think there's anyone who hasn't heard of this phenomena. E is equal to mc squared. What is E, what is m, and what is c squared? Let me explain you. E is energy, that's nuclear energy. M is mass. C squared is speed of light in vacuum squared, which has a value of approximately 9 into 10 to the power 16 meter per second. Meter square per second square. That's too much, isn't it? Yeah, too much. So that's our nuclear energy. Too much. Like I showed you, I have to have a book. The book weighs approximately 300 grams. Let's calculate the amount of nuclear energy it has. 300 grams is 0.3 kilograms into 9 is 2.7 kilograms. 2.7 into 10 to the power 16 joules. 2.7 into 10 to the power 30 kilojoules is the energy inside this, which I'm holding here. When it is not in a gravitational field, right now it's in a gravitational field. So its energy is equal to mc squared plus gh. If I convert all of it into electrical energy, which is a different form of energy, we won't discuss it, then I'll have so much of electricity, which is equal to E, and E is equal to mc squared plus gh. C squared plus gh will give me into the mass, will give me the electrical energy I need. If it 100% goes away, and if I need heat energy from this, I can even get heat energy. So the only energy remaining which we have to discuss is coming back to our main concept of heat. We want to discuss heat energy. For now, I think we'll take a break. We continue after 5 minutes. Enjoy yourself for those 5 minutes.